Let's do an example of degeneracy. Let's consider an eigenstate of a central potential psi sub nlm with energy E sub n. And let's use the fact that the Hamiltonian for central potential commutes with any component of angular momentum. Because of that, the Hamiltonian will also compute with the combined operators L plus and L minus. So that being the case, let's show that we get degeneracy as a result of this. H applied to L minus is going to give me commutator gives me 0, applied to psi n L m, because any component of the angular momentum also commutes with h. So therefore I can say h L plus minus applied to psi n L m can be written as L plus minus h applied to psi n L m, or L plus minus times E sub n, energy eigenvalues psi n L and m. So rotational invariance explains why states that differ only in m have the same energy. Since you have two L plus 1 different values of m, all of which have the same energy. So 2L plus 1, we say in this case, 2L plus 1 is the normal degeneracy expected for cases of rotational symmetry. Hydrogen, which we've studied extensively, also has a central potential, but oddly enough, its degeneracy is not 2L plus 1, it's actually n squared. That comes from a sort of a much more subtle symmetry than rotational invariance. The symmetry is sort of just for completeness, is what we call the Laplace-Runge lens vector, and it's written as m equals p cross L minus L cross p divided by 2m plus v of r times r. So there's this other symmetry that goes with the hydrogen atom that makes its degeneracy not 2L plus 1, but it makes it n squared. This is just sort of a sideline. We're not going to worry about this too much. The most general way to handle rotational selection rules is using the Wigner-Eckhart theorem. We're not going to prove it, but we'll work out the selection rules for the two classes of operators that we encounter most. That is to say, scalar and vector operators. You take a class in graduate quantum mechanics, you'll use the Wigner-Eckhart theorem quite a bit more extensively. Let's talk about selection rules. Let's start easy. Let's do them for scalar operators. For scalar operators, LZF equals 0, L plus minus F equals 0, L squared F equals 0. And we'll do the commutator rules in terms of raising and lowering operators. So let's derive the selection rules by sandwiching f between commutators, such as n, l, m, n prime, l prime, m prime. Now, n, l, m don't have to correspond to the hydrogen atom or hydrogen orbitals. They can be anything is just as long as n, l, m, and n prime, l prime, and m prime are eigenstates. That is to say, of the angular momentum squared and the LZ operator. So, having said that, n prime, l prime, m prime, LZF, and LM, matrix element should be 0. I'll write that out. N prime, L prime, M prime, LZF, and LM minus N prime, L prime, M prime, F, LZ, since they commute, and LM must be equal to 0. What that means then is, in the following way, M prime minus M, N prime, L prime, M prime, F, N, L, M must be 0, since L sub z is Hermitian. So the matrix elements of a scalar operator vanish unless M prime minus M is 0. This is not going to be 0. The product has to be 0, so either this has to be 0 or this has to be 0. If this is not 0, if M prime is not equal to M, then this matrix element vanishes. Simple as that. So what we say then in this case is that delta M, in order for this transition to occur, must be 0. How about for L squared? For L squared, so you have N prime, L prime, M prime, L squared F, N, L, M equals 0. By the same token, so this is going to be, again, N prime, L prime, M prime, and this is L squared F, and LM minus N prime, L prime, M prime, F, L squared applied to N, L, M. And again, applying L squared, the operator, to N, L, and M, that gives me L prime, L plus 1 prime, minus L times L plus 1. So I get this from the left side, this from the right side, times N prime, L prime, M prime, F, N, L, M, again is 0. And the only way this can be 0 is, if I want this matrix element to not be equal to 0, this must be equal to 0. So that tells me, for that to be the case, L minus L prime, which we call delta L, must also be 0. So for this transition to occur, that is to say, for the matrix element to not be 0, L and L prime must be the same. So delta L is the same, delta M must be the same in the case of L sub z. Okay, well, we got one more case to look at, and this is a little bit more messy. Let's look at the L plus case. I may have you do the L minus case for homework. That would be interesting. So this is L plus F and L M. And we write it out the same way. Just as we did before, we can say N prime, L prime, M prime applied to L plus F minus, sorry, N L M minus N prime, L prime, M prime, F L plus applied N L M. That must be 0 as well, since it commutes. Let's use a little, we'll define B sub L M as H bar square root L plus 1 minus M plus 1. We'll define A sub L M as H bar square root L plus 1 minus M plus 1. This is M minus 1 on top. And we can write this then as B L M N prime L prime M minus 1 M prime minus 1 F N L M minus A L M N prime L prime M prime F N L M plus 1 equals 0. Both terms in this equation are going to be 0 unless M prime is equal to M plus 1 and L prime is equal to L plus 1. When those conditions are satisfied, of course, then B L M plus 1 is equal to A L M. That being the case, if that's true, then N prime, L prime, M prime, F, N, L, M must be equal to N, L prime, M plus 1, F, N, L, M plus 1. So the matrix elements of the scalar operator are independent of M. So to sum it all up, we can write it this way: N prime, L prime, M prime, F, the scalar operator, N, L, M, is equal to delta L, L prime, delta M, M prime, N prime, L, double bar F, N, L, whereby the double bars indicate a reduced matrix element and is shorthand basically for a constant that depends upon N, L, and N prime, but does not depend upon M prime. We can do an example of this. It's a little bit lengthy, but it's certainly worth doing. let's find the expectation value of R squared for all 4 degenerate n equals 2 state of the hydrogen atom. So this is for hydrogen. Of course, need the hydrogen wave functions to do this. So what this is saying is the 4 elements are R squared 2, 1, 1, and they should all be equal. 2, 1, 0, R squared 2, 1, 0 equal to 2, 1, minus 1, R squared 2, 1, minus 1. And we'll just, because the m's don't matter, we'll just define this as 2, 1, double bar R squared 2, 1. I want to calculate the reduced matrix elements. Let's pick one of the expectation values. In other words, let's use maybe 2, 1, 0 and calculate the matrix elements. So let's use the 2, 1, 0 case. As we know, if we do it for 2, 1, 0, it works for 2, 1, 1 and 2, 1, minus 1 because n doesn't matter in this case. That being the case, this is going to be equal to integral R squared psi of 2, 1, and 0 of R, quantity squared, dr. Of course, if I put in my hydrogen wave function for R2, 1, 0, I get R to the 4th, R2, 1 of R, quantity squared, dr, times integral of y, 1, 0 of theta and phi, my spherical harmonics, squared omega. Spherical harmonics are normalized so that the angular integral is going to be 1. So this will be 1. The radial wave functions, you can look them up in a table, will give me 0 to infinity r to the 4th, 1 over 24 a cubed r squared over a squared, sorry, e to the minus r over a dr. And if I integrate that through, I'll get 30 a squared. So that would be the expectation value associated with 2, 1, minus 1, 2, 1, 0, and 2, 1, 1. There's one more, that's a triplet state, one more to get. To find the 4th, we just need 2, 0, r squared 2, 0, which I can write as 2, 0, 0, r squared 2, 0, 0, or integral r squared times psi 2, 0, 0 of r squared dr. And that will give me, once again, r to the 4th, 0 to infinity, 1 over 24 a cubed, 1 minus r over 2a. By the way, a is the Bohr radius of the hydrogen atom. E to the minus r over a dr. And that will give me 42 a squared. So I've got 3 that give me 30 a squared, and I've got one more that gives me 42 a squared. And we can do, in Griffiths, there's a longer example where they find the expectation value for r squared in a superposition state. Now, I encourage you to read that example. It's rather lengthy. I don't want to do it here. But I think that it's worth looking at in terms of finding expectation values. Selection rules for vector operators are considerably more complicated, I would invite you to look at the example that Griffiths does regarding vector operators. It utilizes Clebsch-Gordon coefficients. And again, I would like you to spend time with it and work it through. That's what I would encourage in terms of rotation operators. The last topic I want to cover on symmetries is translations in time. So let's move on to the third symmetry. We've talked about translations in space, where we talked about linear momentum, P, the P operator, being the generator of translations in space. We talked about rotations, where the angular momentum operator is the generator of rotations. Now we want to talk about time translations. So suppose capital psi of x and t solves the time-dependent Schrodinger equation. In other words, h applied to psi x of t gives me IH bar d psi of x and t dt. Let's define the operator u of t as the operator that propagates psi of x and t forward in time. So such that if I apply u of t to, let's say, psi of x and t equals 0, that will give me psi of x at some time t. Well, it's easy to express u of t in terms of the Hamiltonian, especially if the Hamiltonian is not a function of time. We'll just use the Taylor series. So I can write u of t psi of x 0 as equals psi of x and t as sum over n equals 0 to infinity 1 over n factorial d dn, dt dn, dtn, I'm sorry, psi of x and t, evaluated at t equals 0, times t to the n. Well, that just becomes sum from n equals 0 to infinity, 1 over n factorial minus I ht divided by h bar times psi of x0. So it's a fairly simple way to do this. If h doesn't depend upon time, all I have to do is exponentiate, and I will get that u of t can be written as e to the minus I ht over h bar. And the Hamiltonian, thus, is the generator of translations in time. By the way, u of t is, if we haven't already talked, I believe we talked about it at the beginning of the course, u of t is also a unitary operator. So this makes sort of a readily accessible way to solve the time-independent Schrodinger equation. Just write out the function at t equals 0 as a superposition of stationary states, sum over n c sub n psi of n of x, and then immediately just say that psi of x and t is just, let's operate it on with the time translation operator, psi of x and 0, and that will give me c sub n u psi sub n t psi sub n of x, which I can write as sum over n c sub n e to the minus I h t over h bar psi sub n of x or sum over n c sub n e to the minus I energy t over h bar psi sub n of x. So if we know it at one time, we can find it at a time in the future. Let's stop with this right now, and we'll continue on. Next time, I believe we will start perturbation theory.